So we've covered the theory behind integration by substitution. What I've got here for you is a couple of examples. I want you to pause the video, read the questions, and then have a crack at them and come back and check you're working with the working I'm going to show you. So here you go. So I've got 3 questions for you. I want you to take all 3 of them, use integration by substitution, and find me a solution for them. So pause the video and have a crack at them. So the first one was the integral of x bracket x squared plus 1 to the power of 5 dx. Now, if we weren't going to use integration by substitution, I could expand this bracket, multiply it out by x, calculate the integral, and then put it all back together. But we're not going to do that. Integration by substitution is a lot easier, as we discussed. What we have to do is first pick something to substitute u in for. Now remember, one of the rules we talked about was that we go for the highest power. Now in this case, the highest power is the x squared. But within that bracket, we've got x squared plus 1. So what I'm going to do is let that whole bracket, the x squared plus 1, be equal to the u. What I'm then going to do is calculate the derivative of it. So I'm going to calculate du by dx. What that's going to give me is 2x. So I then can say, fine, so what I can rearrange that to is du equals 2x dx. So that's me got an x dx here, which I can then substitute in for this. I've got an extra 2, so what I'll do is I'll take it across and write that a half du is equal to x dx. Because what I can now do is substitute all that information in there and end up with a nice straightforward expression which I can integrate. So if I take that, substitute it all back in, I get the integral of u to the power of 5 times x dx, which I can substitute in a half du for. So it's then the equivalent of me saying that I want to do a half times the integral of u to the power of 5 du. Well, we know how to integrate u to the power of 5. That's going to equal a half times u to the power of 6 over 6, then plus c, my constant of integration. Remember, we always include the plus c. Sometimes we're given initial conditions or a condition to use to find it. In this case, we're not. So I've got this here. Now the final step is always to go back to the original variables. So I'm going to substitute back in for u here, simplify and tidy it all up. What I'm going to end up with is 1 over 12 times x squared plus 1 to the power of 6 plus my constant of integration c. So there you go. I've calculated the original expression, i.e. the integral of x bracket x squared plus 1 to the power of 5 dx using substitution. Second question was I want to calculate the integral there of x minus 1, x plus 4, 2x plus 3 dx. Now again, I could multiply everything out and then take each term individually and integrate them. However, there is an easier way to do it using substitution. Now, you'll notice that all the powers here are the equivalent. So all the highest powers are the same. We want to substitute in for a power higher than the powers that we've got. So what I want to do is if I expand these two brackets here, I'll end up with x squared plus 3x minus 4. So my integral will become integral of x squared plus 3x minus 4 times the 2x plus 3 dx. Now if I was to tell you that I'm going to use the substitution u equals x squared plus 3x minus 4, i.e. my new highest power here, and I then calculated du by dx, what I'd end up getting is 2x plus 3. Well look, I've got a bracket here of 2x plus 3. So if I then jig that about, I could say that du is equal to 2x plus 3 dx. So I can use that substitution in this part here. And I can use the substitution for u for this first bit. So my integral then quite simply becomes the integral of u du. Integrating that as we normally would, I get u squared over 2 plus c, again my constant of integration, and then substitute back in for u, and I end up getting a half bracket x squared plus dx minus 4 plus c. Now we could go back to the original expression and factorise this again as well. It depends on what format the answer wants. So I could then have rewritten it as a half, bracket x minus 1, x plus 4 plus a c. So just be wary of that. It may ask for it in a certain format. And if that's the case, stick with whichever one you want. If it's not, again, interchangeable. They both mean the same thing. Third question was calculate the integral of tan x dx using substitution. Now, this seems counterintuitive. We know what the integral of tan x dx is. It's written in our formula list. But it wants us to do it using substitution. Now, all I've got in there is a tan x. So there's no two parts of it for me to substitute in for. However, what we do know is if we think back to work we did back in S1 too, is that tan x is equal to sine x over cos x. So since we can remember that, what I'm able to do is substitute in for one of these and calculate it there. So what I'm going to do is I'm going to say that u is equal to cos x. Now I'm choosing u is equal to cos x because what that'll allow me to do is eliminate the sine x and write it in terms of du, and then write the u with a negative power to integrate using the steps that we normally would. So if I let u equal to cos x, calculate the derivative du by dx, that's equal to negative sine x. So if I rejig this, what I can say is negative du is equal to sine x dx. And if I then substitute that back in for this and put it back into my integral of tan x then quite simply becomes something over u, but that something is my substitution for sine x dx, which is this. So it ends up being negative du over u. I can rewrite that as negative integral of 1 over u du, and we know that the integral of 1 over u is equal to ln. So it then becomes negative ln u plus c. We know that u is the cos x, so substitute back in for it, and we then end up getting negative ln of cos x plus c. So we can use substitution to get the integral of tan x as long as we remember the identity in terms of sine and cos. So substitution, using that for the integration, fairly straightforward. We just have to remember those key rules, looking for the highest power within our expression, or looking for something which can be written as a derivative of another part of it. So bear that in mind when you're working with these sorts of questions.